Hello, this is Ishita, and welcome to the third episode of Explore Space with me. A lot of us know about Sun as the only star, or supernovas or black holes, but how many of us actually know what is the life cycle of a star? A star's long life begins in a nebula, which is a giant cloud of dust and gas. Gravity pulls the nebulous particles together and creates dense regions. As the region becomes denser, it heats up and forms a protostar, which is a hot, glowing mass that is not yet a full-fledged star. The star can either live the ordinary life of an average star, or it can grow into a massive star and decay faster. But first, let's explore the life of an ordinary star. A normal star forms from a clump of dust and gas in a stellar nursery. Over hundreds of thousands of years, the clump gains mass, starts to spin, and heats up. When the clump's core heats up to million degrees, nuclear fusion starts. This process occurs when two protons, the nuclei of hydrogen atoms, merge to form one helium nucleus. Fusion releases energy that heats the star, creating pressure that pushes against the force of its gravity. A star is born. Scientists call a star that is fusing hydrogen to helium in its core a main sequence star. Main sequence stars make up around 90% of the universe's stellar population. They range in luminosity, color, and size from a tenth to 200 times the sun's mass and live for millions to billions of years. When a main sequence star, less than 8 times the sun's mass, runs out of hydrogen in its core, it starts to collapse because the energy produced by fusion is the only force fighting against gravity's tendency to pull matter together. But squeezing the core also increases its temperature and pressure, so much so that its helium starts to fuse into carbon, which also releases energy. Hydrogen fusion begins moving into the star's outer layers, causing them to expand. The result is a red giant which would appear more orange than red. Eventually, the red giant becomes unstable and begins pulsating, periodically expanding and ejecting some of its atmosphere. Eventually, all of its outer layers are blown away, creating an expanding cloud of dust and gas called a planetary nebula. The Sun will become a red giant in about 5 billion years. Once a star burns through all its helium, its outer layers float away into space, creating a colorful, glowing glass cloud called a planetary nebula. This cloud briefly lights up the sky while the star's core, all that's left, shines through from the center. The planetary nebula disperses over time, enriching the surrounding space with heavy elements and dust that can contribute to forming new stars and planets. This process highlights the cyclical nature of stellar evolution, where the death of one star can help birth new celestial bodies. After a red giant has shed all its atmosphere, only the core remains. Scientists call this kind of stellar remnant a white dwarf. A white dwarf is usually Earth-sized but hundreds of thousands of times more massive. A teaspoon of its material would weigh more than a pickup truck. A white dwarf produces no new heat of its own, so it gradually cools over billions of years. Despite the name, white dwarfs can emit visible light that ranges from blue-white to red. Scientists sometimes find the white dwarfs are surrounded by dusty disks of material, debris, and even planets, left over from the original star's red giant phase. In about 10 billion years after its time as a red giant, the Sun will become a white dwarf. Red dwarfs are the smallest main sequence stars, just a fraction of the Sun's size and mass. They're also the coolest and appear more orange in color than red. When a red dwarf produces helium via fusion in its core, the released energy brings material to the star's surface where it cools and sinks back down, taking along a fresh supply of hydrogen to the core. Because of this constant churning, red dwarfs can steadily burn through their entire supply of hydrogen over trillions of years without changing their internal structures, unlike other stars. Scientists think some low-mass red dwarfs Those with just a third of the sun's mass have lifespans longer than the current age of the universe, up to about 14 trillion years. Red dwarfs are also born in much greater numbers than more massive stars. Because of that, and because they live so long, red dwarfs make up around 75% of the Milky Way galaxy's stellar population. Brown dwarfs aren't technically stars. They're more massive than planets but not quite as massive as stars. Generally, they have between 13 and 80 times the mass of Jupiter. They emit almost no visible light, but scientists have seen a few in infrared light. Some brown dwarfs from the same way as main sequence stars from gas and dust clumps in nebulae. But they never gain enough mass to do fusion on the scale of a main sequence star. Others may form like planets from disks of gas and dust around stars. But let's rewind back to the part where we discussed the fate of a protostar. So what's the life of a massive star, a gigantic star, like? Massive stars burn through their hydrogen fuel much faster because their cores have higher pressures and temperatures. This makes their main sequence life much shorter than average-sized stars. As a result, massive stars evolve quickly, transitioning through various phases before ending their lives in a spectacular supernova explosion. Their rapid evolution also means they are crucial in enriching the interstellar medium with heavy elements essential for forming new stars and planets. After millions of years spent in the main sequence, a massive star uses up all the hydrogen fuel in its core. As a result, the core shrinks, gets hotter, and starts burning helium and other heavier elements. This process makes the star swell up into a huge red supergiant. This stage does not last as long as the main sequence, but it's important because it creates elements heavier than helium. Betelgeuse, for example, is currently in the later stages of its stellar evolution. It has already exhausted the hydrogen in its core and expanded into a red supergiant. Located about 700 light-years away in the constellation Orion, Betelgeuse has a radius roughly 1,400 times that of the Sun. Due to its massive size, Betelgeuse will likely end its life in a dramatic supernova explosion, a fate typical for stars of its kind. One type of supernova is when the core of a massive star begins to produce iron. It can no longer create energy anymore because iron uses up energy instead of releasing it. This causes the core to collapse under its own weight. The result is a supernova, a huge explosion that is so bright it can briefly shine brighter than an entire galaxy for days or even months. As we have discussed earlier, stars are stable celestial bodies. The inward force of gravity, which has a tendency to collapse the star, is balanced out by the extreme outward pressure of the nuclear fuel in the star's core. However, when a massive star runs out of fuel, it cools and the pressure drops. Due to this extreme force of gravity, the star suddenly collapses. Imagine a body about 1 million times the mass of the Earth collapsing in about only 15 seconds. The collapse happens so quickly that it creates enormous shock waves that causes the outer part of the star to explode. Another type of supernova is a type 1a supernova, which is a supernova that occurs in binary systems, two stars orbiting one another, in which one of the stars is a white dwarf. The other star can be anything from a giant star to an even smaller white dwarf. If one white dwarf collides with another or pulls too much matter from its nearby star, the white dwarf can explode. After supernovae of such types, the dying star can have two fates. Either its heavy core is left behind as a neutron star or something much denser, dark, empty, and scary. A black hole. Neutron stars are stellar remnants that pack more mass than the Sun into a sphere. A neutron star forms when a main sequence star in between about 8 and 20 times the Sun's mass runs out of hydrogen in its core. The star starts fusing helium to carbon like lower mass stars. But then, when the core runs out of helium, it shrinks, heats up, and starts converting its carbon into neon, which releases energy. This process continues as the star converts neon into oxygen, oxygen into silicon, and finally silicon into iron. These processes produce energy that keep the core from collapsing, but each new fuel buys it less and less time. By the time silicon fuses into iron, the stars run out of fuel in a matter of days. The next step would be fusing iron into some heavier element, but doing so requires energy instead of releasing it. The core collapses and then rebounds back into its original size, creating a shock wave that travels through the star's outer layers. The result is a huge explosion called supernova. The remnant core is a super-dense neutron star. Neutron stars are usually of two main types, pulsars and magnetars. Pulsars are a type of rapidly rotating neutron star. Bright X-ray hotspots form on the surfaces of these objects. As they rotate, they blast out pulses of radiation at regular intervals ranging from seconds to milliseconds. Some pulsars spin faster than blender blades. According to the University of California, because the poles of the magnetic field aren't aligned with the axis of spin of the pulsar, the beams of particles and the light they produce are swept around as the pulsar rotates. All neutron stars have strong magnetic fields, but a magnetar can be 10 trillion times stronger than a refrigerator's magnet, and up to 1,000 times stronger than a typical neutron star. The density of the interior of a magnetar is such that a tablespoon of a substance would have a mass of over 100 million tons. Most observed magnetars rotate once every 2 to 10 seconds, which is less than pulsars. A magnetar's magnetic field gives rise to very strong and characteristic bursts of X-rays and gamma rays. Their strong magnetic fields decay after about 10,000 years, after which activity and strong X-ray emissions cease. Given the number of magnetars observable today, one estimate puts the number of inactive magnetars in the Milky Way at 30 million or more. Thank you for watching this video to the end. We come to the end of our lesson. Please like, share, and subscribe to my channel. And please also check out my website.